Let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another session of Math 1000. Hopefully you guys had a good week. Let me share my screen here and we can get started. And let me make sure that I'm seeing the chat. Okay. All right, so I believe we're good. Okay, all right. So the agenda for today, as you can see here, quiz 2, the questions from quiz 2 are up on the screen. Maybe I can make this a little bit larger. So the plan for today was to go over quiz 2, making sure that everyone's on the same page and we all know why the answers are the answers. And then we're going to have a little Q&A. I will say though, in my first class, we actually didn't get to the Q&A part because there were actually a lot of questions on the quiz itself, which is good. It's good that we can get to deal with whatever issues that you guys might be having. And some of these are really sneaky because if you're not paying attention to the rules that we've developed in class, it's very, very easy to make a mistake because one rule to the next, they're all very simple applications at this point, simple little operations that you have to do. So it's really easy to mess up one simple operation with another simple operation. So just knowing like, when do you add powers versus multiplying powers, things of that sort, you really have to have under control. Otherwise, you'll get into a lot of trouble. And a lot of issues arose in the last class because of that. So let's see where we are in this class. So let's actually just jump right in. So I pasted the questions here in this OneNote, and as always, I will be sharing a copy of this document with you guys when I post the video. So that being said, I'm not going to do the polling thing that I did last time, so I'm pretty much going to go through the quiz. As I'm doing the questions, I might ask for input, or if I'm just going through something, you can stop me at any point, so don't be afraid to interrupt or ask a question, and also don't be afraid to participate if I asked for some input. So that being said, let's actually just jump in and get through this quiz, and then we'll play it by ear. So 1.1. So problem 1 was just going over some rules, so that had 5 parts to it. And these were just things that you just should know. So it's not necessarily things that you had to calculate or figure out. You should just know these based on rules that we've been doing in class. So 1.1, a to the power x over y. What is that? It's asking for input here.
The root of y root a to the x.
Correct. So that would be that one, right? So that was the flower power, right? So the bottom is the root, the top is the power. So you get flower power. So that was that one. 1.2, if I have m to the x plus y, so I'm adding the powers, what is that equivalent to?
M to the xy power.
You think it's this one?
Yes. Wait,
Okay.
no, the third one.
The third one, okay. All right, good, catching your own mistake there. Great. So it's when you multiply things of the same base, you add the powers, right? So that was actually something that came up in the last class, so just be aware of that. You add the powers when you're multiplying things of the same base. What about a to the minus n? What is that equivalent to?
1 over a to the n.
Correct. So a negative power just means reciprocal. So that's that option right here. What about m squared minus n squared?
None of the above.
None of the above. Can you actually tell me what that is equal to? If you were to complete a rule for that, what is that? So it's none of the above. What would a possible answer be?
M parentheses m minus n parentheses m plus n.
Right. So that is this. What's that called? The name for that?
Difference of squares.
Difference of squares. Right. So difference of squares or difference of two squares for emphasis, but it's the difference of squares formula. So whenever you see a difference of squares, you should know that you can factor it into something that looks like that. That n looks like an r. Let's fix that. Okay. M cubed plus n cubed. Which one is it?
None of them.
None of the above. What is the actual formula?
M plus n on parentheses, open parentheses, m squared minus n plus n squared.
Right. So it's actually a very common error to put the 2 in there. So this would be a common error. Right? And that's an error that students often make because of that other formula, a plus b all squared is a squared plus 2ab plus b squared. So whenever anyone writes 3 terms like that where the ends are squared, there's this itch to put a 2 on the middle term. Don't fall into that trap. It applies to the perfect squares formula. So make sure that you don't accidentally throw a 2 in here. It's actually very, very common to do that. So back when this was in-person classes and I would ask this on a quiz, students would literally write in the 2s as an answer, right? So it wasn't multiple choice back in at that point. So don't write in the 2s. Okay, this one requires a little bit of calculations, not a lot. So this is not some generic formula that you should have memorized, but there is a process that you should memorize here. The GCF, which is the greatest common factor. How do we find the greatest common factor? What is the answer here?
3x to the negative 1/2.
3x to the negative 1/2. And can you tell me how you came up with that option? Like, what did you think, or how do you describe what that is?
Well, you can take out a 3 because all the factors are multiples of 3. So you can take out a 3. And then the lowest power of all of them is negative 1/2. So you take out a 3x negative 1/2.
Right. So the idea is the GCF is the product of all common factors raised to the lowest power to which they appear. Right. So that's how you find the GCF. So if you look at the original, this guy was equal to 3x to the 3 over 2 minus 3 squared x to the 1 over 2 plus 2 times 3 x to the minus 1 over 2. You'll notice that there are 2 common terms. So there's a 3 in everyone. And there is, let's look another color, blue. There is an x in everyone. Okay. So 3 is a common term, x is a common term. You want to take a product of all the common terms, then you raise them to the lowest power to which they appear. So 3 appears with the power 1 and the power 2. So you actually pick the power 1, so that's just 3. And the x appears with the powers 3 over 2, 1 over 2, minus 1 over 2. The lowest power of these is the minus 1 over 2 because it's a negative, right? So it's automatically lower than the other 2. So product of all the common factors to the lowest powers to which they appear gives you the GCF. All right. Okay, let's move on to the next one. So this one requires a little bit more computation, but still, I guess, not a crazy amount. So what do we do here? So here's something with 3 terms. What do you want to, how do you start off the factoring process?
Can you take out a 2 to the 2x to the negative 1/2?
Right, so the GCF in this case is 2x to the negative 1/2 for the same reasons that the 3x to the minus 1/2 was the GCF in the previous problem. So 2x to the minus 1/2. And what do you write out on the inside? What's left over?
Can you put x to the first power? And then 4, wait, yeah, 4, and then negative x to the negative second, is it? No, that's not even answer choice.
No, there's an issue here. So the first issue is with the coefficients, right? You had a 2, 4, and a 2. You factor out a 2, which means you would be left over with a 1, a 2, and a 1, right? So the middle coefficient should definitely be a 2. Right? So there's a 1, which you're not going to see here, but let me. You're going to left over with a 1 because the 2 times 1 is going to give you back that 2. The 2 times the 2 is going to give you back that 4. And then there's a -1 here, 2 times a -1. Now, your powers on the x's were also not correct. How do we get the correct powers?
Because we've taken a factor of -half, we subtract half from all of the powers. So
you subtract the -1/2, right? So you subtract the power that you pulled out. So we pulled out a -1/2, so the new power is going to be the old powers minus that -1/2. So this one is going to be the old power minus the -1/2. This is going to be the old power minus the -1/2. You subtract the power that you pulled out. So now that power is going to be 3/2 plus 1/2, which is 4/2, or 2. If I take that 1/2, oh, still have someone trickling in here. The 1/2 plus 1/2, so that's just going to be 1. So this here is 2x to the first power. And then I have the -1/2 minus the -1/2. That's just x to the 0. X to the 0 is 1. That's a law of exponents. So that. Now we have to check, does this factor further? So you factor out the GCF, and then you want to make sure whether or not what you're left over with factors further. Does that factor further?
No.
How would you check? What did you check to, how would you check?
I did what multiples multiply to -1 but add to +2.
Right, so you need 2 numbers that multiply to give the -1 and add to give the 2. Okay, can you think of 2 such numbers?
No.
No, right? So no, right? No such numbers. So this doesn't factor any further, which means that's your answer right here. And then we look if that is possible. That is the full factorization, and that's this option here. Okay, awesome. And again, if any of you have questions on what we're doing so far, don't be afraid to stop me. I'll just assume that everyone's on the same page and move on, unless you guys stop me. So, okay, let's keep going. How would you simplify this? Right, so I start off with the 3cd to the 6 cubed, cd to the 4th.
First you would I guess distribute the exponent, which is 3, so it would be 3 squared c cubed, c cubed, and then d to the 6 times the 3.
Shouldn't that be d to the 9?
Yes, you would add the exponents.
Would you?
No, you multiply.
No, you multiply.
You made me trick you. Don't do that. Like, you said the right thing the first time. It's multiply, right? So you have to multiply the powers, right? So remember, the rules are, if you have x to the a and there's a b outside, you multiply, right? And the rule for adding comes when you're multiplying things of the same base. That's when you add, right? So we saw that earlier. But don't do that. Every now and then I'll play devil's advocate, because what you'll find happens is that this happens on tests to students a lot. Like, they'll write down an answer, but then they start questioning themselves, right? They'll be their own devil's advocate. So you need to know what you know so that you don't talk yourself out of the right answer when you're in a testing situation. So so sometimes you'll tell me the right answer and I'll be like, wait, are you sure you shouldn't add that? Just to see, do you know what you know? Don't let me do it. And don't do it to yourself either. Someone else is trickling in here. Let me let them in. Okay, so you have to multiply the powers here because of the laws of exponents. You only add the powers when you have the same bases being multiplied. So that's what the first thing comes in as. And again, we're doing this because of PEMDAS. PEMDAS says work out the thing that's in the parentheses first. There was nothing to work out in the parentheses. It was pretty much as simple as possible. So the next thing is the exponents. So now we have to simplify all the exponents. For the similar reasons, this here is d to the c to the fourth, d to the fourth in that. Now with this, because these two factors are as simple as they can get, what I would do is just, you can remove the parentheses here without consequence. Maybe I'll just take the opportunity to write this as a 27. So that's the 3 cubed right here. That's the 27. Okay. Now what?
Can combine like terms.
How?
Add in the exponents of common bases.
Right. So for one, and this is a separate step, you don't have to write this down technically, but I just so that everyone understands, because it's multiplication, I can rearrange terms without consequence. And then the rule takes effect that I'm multiplying things of the same base here. So then that would become c to the, I add the powers, so that's 7. D to the add the powers, 22. Right? And that's the answer. And that's this option here. Okay, awesome. Let's keep going. Choose a possible middle term so that this thing would factor. So I have x squared plus blank plus 20. What is a possible middle term?
12x.
12x.
12x. How did you figure that out?
I did. Oh, I don't know. I forgot.
Right. So, but the idea was we want two numbers that multiply to 20. But sums to give. And a priori we don't know, but it's 12 or 13 or 7 or 3 or minus 10. But here you'll see that 12 can work out nicely because you can use 10 and 2. But if you try a bunch of combinations, you'll realize that none of these other ones work. And so choosing 10 and 2 can make it work. And so that leaves us with 12. There are other ways to do this. That's one way to just check the rule that you know how to factor a trinomial. Was someone saying something?
I was gonna say, yeah, I thought of factors of 20 that would add up to make the middle term.
Yeah. And whenever you're not sure how you would choose the factors, it's probably also best to go down to the prime factorization level. So 20, it's actually 2 squared times 5, right? So there are a bunch of ways that you can break that down. You can take the 10 times the 2. You can also take the 4 times the 5, right? You can also take the 20 times the 1, right? So these were pretty much all the factors that we could use here, just using a combination of 2 2s and a 5. I can multiply the 2s and leave the 5, that's the 4 times the 5. I can multiply the 5 and a 2 and leave a 2, that's the 10 times the 2. I can multiply the 5 times the 4 and get the 20 and leaves a factor of 1. So these were really the options that I had here, right? And with those numbers, 10 and 2, 4 and 5, 20 and 1, the only one that was possible here was the 12, right? Yeah, okay. And so far we're moving faster than last time. We might actually have some time for a Q&A at the end, or maybe I'll do the bonus with you guys. Okay, another one, some common errors are normally made with this guy. 5x to the minus 2, what is that equivalent to of the options here? Or if any, maybe it's none of the above.
5 over x squared.
5 over x squared. I will mention here that this and this are very common errors.
Can you explain why it wouldn't be 1 over 5x squared?
Right. The reason is the exponent notation only applies to the thing that's immediately to the left, unless you indicate otherwise with parentheses or something. So when you see like a 5x to the minus 2, you think of this as 5 times the x to the minus 2. The minus 2 only applies to the x, the minus 2 power. So this leaves you with 5 times, if you apply the laws of exponents, that's 1 over x squared. And then when you multiply the fractions, you get the 5 over x squared, right? To actually move the 5 into the denominator, what you're saying is that the negative power influenced the 5, which it doesn't. Something like the last one, this would actually be if I had 5x in parentheses to the minus 2. And so that would be 1 over 5x squared, and that would be 1 over 25x squared, right? So the lack of parentheses tells you that the 5 should be left alone, right? So the 5 is going to stay there in the numerator, and 5 you can always think of as 5 over 1. So you know it's staying in the numerator. The minus 2 does not affect the 5, right? So the notation of parentheses, it applies immediately to the left, unless otherwise indicated by parentheses or something. So that's why the third option is correct. You leave the 5 alone, you apply the negative second power to the x. Okay, which one are we equivalent to now? Minus 18 in parentheses raised to the negative 18.
It will be 1 over x to the 18.
Yes, that's the first one. Bonus example. Okay, what if I had minus x to the minus 19? What would your answer be?
One over negative x to the 19.
Right, so that one you'd keep the negative power, right? Which was that option here was kind of teasing you to do that. But because the negative 18 is even, that got rid of the negative sign. So this one here, again, applying the laws of exponents, this is 1 over, it's like my negative x is the a. So this is 1 over negative x to the 18. Law of exponents will say I can distribute the 18 to the negative 1 as well as to the x. Negative 1 to the 18 is just 1, so this is just your x to the 18. Right? The even power is going to get rid of the negative, which is going to be very important for a problem that we will see soon. knowing that even powers get rid of negatives, it's going to make for a little bit of a nuanced approach to a problem that's coming up. This one, how do we do this one? So this one's going to require a bit more calculation than the last two parts. So let's actually write this down separately. So let's say I had 4r cubed, r to the 4th cubed, over 15r cubed minus 2. All right, what do I do first?
You multiply the r to the 4th and the 3rd power, so turn to 4r cubed times r to the 12th.
Correct.
Over,
right, so again, PEMDAS means we're simplifying the exponents first, because what's in parentheses is already simplified. So the next thing is to worry about the exponents. Simplify all the exponents, and we have that. And for similar reasons, this here would be minus 15. Now what?
oh, it's minus 16, minus 6, sorry. It's 3 times 2.
Minus 6, yes. Don't know where 15 came from. Oh, it's
And
because
now,
I already started doing the top in my head. Yeah.
Yeah. 4 times r to the 15 divided by 15 r to the negative 6. So it will be 4 r to the 15th plus 6 because it's minus negative 6.
Right, and in fact, you can actually think of the constants. Think of this as multiplication. You think of these guys separately. So you can actually think of this as 4 over 15, and then the r to the 15 over r to the minus 6. You just apply the laws of exponents here.
And you end up with
So it's
4r to the 9th.
You'd end up adding the 6, yeah?
Yes.
So that's 21. So it's 4r to the 21 over 15. Do we have that option? Yes. Now, someone mentioned last time about switching the roles. So you can take that r to the negative 6 in the denominator and move it up. So some of you might have been thinking of that. And that's a kind of maneuver that I see students try to apply all the time. And in a situation like this, you won't really get in trouble with it. However, when you have many terms and you start doing things like that, like knowing that a negative power means you can switch the position from the numerator to denominator or vice versa. Or if I have a fraction raised to a negative power, I can flip the fraction on the inside and change the power to the positive. So maneuvers like that where you're moving positions, when there are a lot of variables and students start trying to move positions while they're trying to apply laws of exponents, they tend to make a lot of errors with that. So I really would encourage you to, instead of thinking of switching positions based on negative powers, I would much rather you do things like add the powers, subtract the powers, and just keep it with the basic arithmetic operations. So it's you can get yourself confused when your brain is trying to do two things at once. So you're trying to switch locations and you're trying to add and subtract powers. Just do one thing at a time. Just add or subtract the powers and don't worry about where the locations, because the location will, once you add and you get the power, that simplified power will tell you what location you should be in. If it's negative, you know you can move it to the bottom. If it's positive, you leave it where it is, right? So I would first simplify everything before worrying about changing positions and anything of that sort. So that would be what this would look like. Okay, what does this simplify to? Square root of 144 y to the 6th.
12y to the 3rd.
Which one? 12y to the 3rd?
Wait, no, sorry.
Isn't
It will
that
be,
value?
yeah, the
Come
absolute
again?
value of y 3rd.
You need the absolute value. Right? So this was something that was mentioned in class. So you should recall the square root of x squared was equal to the absolute value of x. This was in fact an alternative definition. It's an important definition. You should remember the main definition of absolute value of x though, and especially in calculus 1 and beyond, it's going to come up all the time. So it's x if x is positive, it's 0 if x is 0, and it's minus x if x is negative. And you'll realize that what the absolute value does is it keeps things positive. So if I plug in a negative value into the absolute value, it returns the positive value of the same magnitude. If I plug in 0 into the absolute value, it returns 0. If I plug in a positive number into the absolute value, it just gives me the same number back. You'll realize that whenever you take the square root of x squared, the same thing happens, right? So note, if I take the absolute value of 1, I get 1. If I take the absolute value of -1, I get 1. Whereas if I take the square root of 1 squared, I get 1. And if I take the square root of -1 squared, I get 1 again. They behave the same.
I have a question about that.
Yes.
Why does the square root not put onto both -1 and 1 squared would give you 1? So why does the square root only give you the positive?
The square root gave me the positive because of the square, right? The square is what made the thing positive.
I also have a question. So instead of
right, there's a -1 and then I squared it and then I took the square root of that. So the -1 squared is +1 and then I square rooted +1. So I get +1.
I have a question.
Yes.
Instead of writing the absolute value, because like if you take the square root of 144, can't you just write plus or minus 12?
No, because the square root is, also recall, the square root that we use is the principal square root. Recall, when we look at y equals the square root of x, we're looking at this graph right here. It only has a positive part. There's no negative part. Right, so the square root of x is always going to be a value greater than or equal to 0. So the square root of 12 isn't plus or minus 12.
So what would
right?
it
And that's a common error. So where that idea comes from, and this is also relating to something else I mentioned kind of towards the end of the class that you should have watched for this quiz, where I mentioned there's some things that you're allowed to do when there's an equal sign, and then there are some things that you're not allowed to do when there's not an equal sign. So the reason why a lot of students will think that it could be a plus or minus 12 is because they've seen scenarios like where if you had, say, x squared equals 144, then you would say the x is equal to plus or minus 12. And that is correct. But it is not because the square root of 144 is plus or minus 12. The reason was because this is equal to that, which is equal to this. And so you get x equals 12 or x equals minus 12, right? So there was a whole process that happened behind the equal sign. So it's like, if I wanted to know what numbers can I square to get 144, I can take a plus or minus value. However, if I'm taking the square root of 144 and I'm not concerned with where that 144 came from, the negative value is no longer on the table, right? So there's a difference whether you're solving an equation versus you're just taking the radical of something where there is no equation, right? A plus or minus comes into play when there's an equation. If there's no equation, you only take the positive value. For us, the square root, the graph looks like that. There's no negative part. There's no part down here. That being said, you might be wondering why, if I have the y to the 6th, do I have to get the thing? So let me explain that a little more. So the above, so square root of 144 versus this, right? So this only take positive value. since no equal sign, because that might be right. So now the above means if I'm taking the square root of y to the 6, what I can think of that as is y squared times y squared times y squared. We know the laws of exponents means that I can actually distribute the square root across these three. By definition, that's absolute value y, absolute value y, absolute value y. And so you get absolute value of y cubed, which is the same as absolute value of y cubed. Right, so yes, when you take a square root, it means raising something to the half power. And so you might just decide to multiply the powers according to the rules. However, because the even power can make things positive, which is the nuance that I mentioned a little bit earlier that is going to come up, because of that, it means that there is a little bit of adjustment that needs to be made with things like these. Because now if your y is negative, it will still output the positive value. So it's going to behave like an absolute value. So there's a little bit of nuance in how you apply the rules here. Once the power is even, you have to be aware that, oh, now negative values, they're all out. Negative values can't happen anymore because of the even power. I'm raising something to the 6. So negative values are gone, which means this thing is going to behave like an absolute value. Right? So you'll notice that in the first one, if I plugged in y equals -1, the answer would be positive 12. Whereas here, if I plugged in y equals -1, the answer will be negative 12, which means these two are not the same thing, right? So notice here, this, not the same. To see this, one example, set y equals -1. If I take the square root of 144 times -1 to the 6, I would get 12. Versus if I take 12 times, plug in a 1 here, cubed it, I get -12, not equal. Right? But that is a common error. And it's because students often forget the squared, the even root of something raised to an even power is equivalent to an absolute value being there. And yeah, so that was something that was discussed in class. I just wanted to make sure that you guys are aware of that. Okay, so now we are going to simplify radicals. So in class, I told you guys a strategy that I think is very nice for problems like this. Pretty much when you want to simplify a radical, you're going to open up 2 radicals in place of that radical. You throw everything that simplifies into the first radical, leave everything that doesn't simplify into the other radical. So if I were to have I would immediately open up 2 radicals in place of that 1 radical. You can do the same here, although it's not going to make a difference. It's unnecessary here, as we'll see. And pretty much you just break things into factors. So you look at the x to the 10th, for example, you take each factor, and then you're like, okay, how can I split this into a product of 2 factors such that one of them will simplify under a 9th root while the other one won't, right? So you try to break up x into 2 powers that when you multiply them, you get x to the 10th, but you separate it in such a way that 1 power is divisible by 9, and it's the largest possible part of 10 that divides by 9, and then the remainder is left on the other one. How can you split up x to the 10th here?
X to the 9th and x.
Right, you can split x to the 10th into x to the 9th and x. I put the one that simplifies into the first radical. So put terms that simplify. And simplify here has a very specific meaning. Simplify means the power is divisible by the number on the radical, right? So the power 9 is divisible by 9, so that's why it goes there. The power 1 is not divisible by 9, so I leave it over in the other one. Similarly, if I were to split y into two parts, well, nothing simplifies here, and just y to the 1, the y would stay. So it kind of means you don't have to do anything. So you don't even have to notice the y here anyway, right? Because that's just 1. So for the similar reasons, this one will break up into x to the 0, y to the 0. So for that reason, you can ignore, since you're multiplying by 1. And so the x and y will be left over here. And so what you'll have here, to clean up a little bit, okay, and what is the 9th root of x to the 9th?
X.
It's just x, not the absolute value of x, right? So the absolute value, remember, comes in when there's an even power. So maybe I should actually state that. I did state this in class, but maybe I should state it again for the record here. So what this means is if I take the nth root of x to the n, it's equal to the absolute value of x if n is even, but it makes no difference if n is odd. It'll just be x if n is odd. And that's because if I raise a negative number to an odd power, it stays negative. Then if I take an odd root of a negative number, it stays negative. So it'll keep the sign of the original. So the 9th root just becomes x, not the absolute value of x. And so now I have that. So now I have 5x to the 9th root of xy minus 4x to the 9th root of xy. How can I simplify that?
Subtract, because you jump. It's the 9th root xy and the 9th root of the xi are the same. Right. So you just care.
These guys are the same, right? So it's like 5 apples minus 4 apples. You're left over with 1 apple, right? So you're just left over with x to the 9th root of xy, right? So it's like if you were to call this a, so this is like 5a minus 4a. Well, the answer is just the a, right? And so you have that. So that would be the answer, and that is option C, B, it looks like. Let's do a bonus example here. Let's say I wanted to do something like, if I say to simplify that, how would you do it now? So you'd break things up into 2 radicals. So I just want to make sure that you guys have this down, like how to actually split the radicals and place things. So maybe someone can tell me how you'd split things here. Maybe someone who hasn't really responded before me can give it a shot. go through one factor at a time. 64. How would you split 64 into two things? Where you multiply them, you get 64. But if you, one of those things is you can take the fifth root of it. I'll even give you a hint here. 64 is the same thing as 2 to the 6th power. So if you have 2 to the 6th, how can you split that into two parts where one of those things you can take a fifth root?
It'll be 2 to the 1 and then 2 to the 5th.
Okay. So you put 2 to the 5th in the first one, 2 to the 1 in the second one. So remember, factors that simplify go here. Simplify equals the number on the root will divide into the power, and it is the largest possible power. We'll see where the largest possible power part comes up pretty soon, but let's move on. What about the x to the 23? How would you break that up? X to the 23, how would you break that up?
Will it be x to the 20 on the first one and then x to the third on the second one?
Right. Now here's what I meant by the largest power idea, because here's another way that we could have broken it up. I could have said something like x to the 15, and then on this side I would put 8, right? Now why would that not be the way to go? Because you'll realize that x to the 8th can be simplified further. I can get an extra 5 factors out of that, right? So there was a way to break this down so that's even smaller, even simpler. There's more stuff to simplify. So the 15 is not the largest possible power, that the largest possible part of 23 that is divisible by 5, right? So it's very important that you pick the largest possible thing, where what's left over is actually smaller than the root. So factors that don't simplify here, factors that do not simplify go here, meaning their powers are smaller than the number on the root. Okay, so if I had broken it up into like x to the 15 and x to the 8, it would not satisfy the fact that x to the 8 can be simplified further. 8 is bigger than 5, and I have the 5th root, right? So this would be broken down into 20, x to the 20 and x cubed. 3 is smaller than 5, so that's pretty much, that's the best option. Similarly, this would be y to the 15 and y to the 1. And again, there are a bunch of ways that I could separate the y's. I could do y to the 10th and y to the 6th, but y to the 6th can simplify further. So it's y to the 15, y to the 1. What about the z to the 35?
G to the 35 on the first one, and then
Right.
z to the 0.
Z to the 0 on the other one, and you don't even have to write it at this point. There's an invisible z to the 0 here, right? Once you get there, now you can go through and you can take the 5th root of everyone. How do you take the 5th root? Just remember the 5th root is just the 1/5 power. So I'm just going to go through and multiply all the powers by 1/5. And then this radical here is left over. That's 5th root 2x cubed y. And that would be the simplification. Okay, so simplifying radicals comes up ever so often, so make sure that you understand how to actually do that. Tons of strategies on how you can do this, but I think this is one of the easiest ones out there to actually follow. So you want to simplify stuff under a radical, you break the radical into two parts, throw all the factors that simplify into one, leave everyone else on the other one, and you can simplify the first part and leave the last part. Okay, 8. I have an expression with 3 terms. I want to factor it, right? So I give you an expression with 3 terms. That's all you know at this point. You have no other information than that. What is the first thing you're going to try to do?
Find the GCF.
Good. Find the GCF, which means it's technically none of the above here. Right? So this was a problem that I put on the last quiz, and the option to find the GCF was there, and that should have been what was selected. And then I used that opportunity to re-emphasize that finding the GCF is always the first thing you want to do. Now, a lot of students, I realize here, pick something like the AC method or something else. And the thing is, technically, you don't know that because you don't even know if the expression I gave you is a quadratic. The AC method works with a quadratic where the leading coefficient is not 1. So you can't really apply that with the given information. What you do know is the first thing you would do without any information given is try to find the GCF. So first, try to find the GCF. And even if you had quadratics, this would be one of the first things you would do. So if I had like 2x squared plus 4x plus 2, even before I tried the AC method, I should notice that there's a common 2 there, and I should factor that out first. Because you'd realize that I won't even need the AC method at the end. This is just the perfect square. So try to factor out GCF is the first thing. Always the first thing. It's always the first step in a factoring problem. So just so you're aware of that. Always first thing. So you have to factor something before you apply any technique. First, look for common factors to factor them out. Okay, 9. Okay, so I spoke about a problem similar to this in the review. So let's actually go through this. So in the review, I discussed the problem y to the 6, x to the 6 minus y to the 6. Here I bumped the powers up to x to the 12th and y to the 12th, but the same kind of concept should work. So what is the, so given this specific problem, what's the best first step?
Difference of squares.
Apply the difference of squares, right? So it's the best first step is not the GCF because there is no GCF. You can look at it. You don't know if x and y have any common factors, so there's nothing for you to pull out. There are 2 options that are viable. You can think of the powers as 6 times 2 and then use a difference of squares formula, or you can think of the powers as 4 times 3 and use the difference of cubes formula. And as we discussed, applying the difference of squares is going to be the better option. Because you're going to, if you go the other way, you're going to end up with a factor of x to the 4th plus y to the 4th plus x squared y squared, and that actually factors further, but you're actually not going to notice it. Here. So that is that. So that was something that we discussed in the review session before, so I won't go any more into that. Now 9.2 actually had you try to factor it fully, and then tell me how many factors you had. So here we're actually going to go through the process of factoring x to the 12th minus y to the 12th. And as was from the first part, the better option is to look at it this way. So with that, now it looks like the difference of squares, which means I can break it down to x to the 6, y to the 6 times x to the 6 plus y to the 6. In the first one.
Is there a reason you're using square brackets instead of?
Because I'm going to throw in some more parentheses later. So
okay.
I want to. So there's no reason to use square brackets. I could use parentheses everywhere, but sometimes when I'm doing nested parentheses, I like to put the outer ones as brackets and the inner ones as parentheses for aesthetic reasons. So here again, the x to the 6, y to the 6 is the problem that we discussed before, so that I would think of x cubed squared and y cubed squared. Now for this part, there is no sum of squares formula. So the only option here is to actually think of this as a cube. And so here, what I can have is x cubed minus y cubed times x cubed plus y cubed. And here, applying the sum of cubes formula, which we earlier in the quiz, we had to do that. So this would be x squared plus y squared, which doesn't factor any further, times x to the 4th minus x squared y squared plus y to the 4th. The first two, here I can apply the sum of cubes formula to the x cubed minus y cubed. I can apply the difference of cubes formula, excuse me. Then I apply the sum of cubes formula to the x cubed plus y cubed. And these guys are just left over. And now we count the factors. 1, 2, 3, 4, 5, 6. So that was that one. Problem 10. So problem 10, I believe, had 3 parts. Okay, so this one, it's just something to know. I guess you could FOIL it out, but you should really just know this by heart, actually. Perfect squares. X plus y all squared is x squared plus 2xy plus y squared. Okay, awesome. Now in part 2, I asked you to use that principle. I guess, or otherwise, you could figure it out as well. To factor this thing, a squared plus 6ab plus 9b squared. And I mentioned, and this is a hint that I spoke about in class as well, is to just ignore the second variable for at first, because you'll actually see it a lot easier. So if I looked at it as a squared plus 6a plus 9, I can realize that that was a perfect square. Okay, because the middle term looks like 2 times a times 3, and the 9 is 3 squared. So it follows the pattern of the last one. You can also do the thing where you find 2 numbers where you multiply, you get 9, you add them, you get 6. So you get that. And then what you do is you just attach the b after the fact to the second term. And that would actually be the factoring. And that is here. Now, in the third part, I asked you to do a weird factor by grouping thing. But it's not going to be applied like the traditional factor by grouping, because for the traditional factor by grouping to work, when you factor things out, you should be left over the same thing. That wouldn't happen here if you pair things off. The idea was I expected you to group it based on the previous problem, which means you'd group it into this and that. So the idea is if I have a squared plus 6ab plus 9b squared minus 49, I would think of this, well, this part here, think of it group this way, group this way, because we dealt with the left group earlier. So this is a classic mathematician, oh, let's solve a more complicated problem based on our solution to a simpler problem. Okay, there's a joke about that, but I'm not gonna, okay. All right, so we learned that this first part factored into that. Given that, how can we proceed? Do you guys see what we can do here? What would be your approach here? The goal is to factor. Do you see anything you can take advantage of?
It's the difference of squares.
Difference of squares. 49 is actually
7 squared.
7 squared. So it's the difference of squares. So I can break this down into the first thing minus this times the first thing plus that. So that gives me a plus 3b minus 7 times a plus 3b plus 7. And that is the first option. Okay, and so at this point, that covers all the problems I would expect you to know. But a lot of you probably know how to handle the bonus problems as well, so maybe I'll just go through those quickly. Okay, so first one, 11.1. I gave you this equation, x minus 1 times x minus 2 equals 12. What is the first thing to do, the best first step? Do I set x minus 1 equals 12 and x minus 2 equals 12? Do I set these equal? Do I divide both sides by 12? Which of these do I do first?
I said none of the above.
None of the above. What would you do first?
Distribute out the
Right, expanding the parentheses would be the first step. So it's actually none of the above.
I forgot what that was called for a second, but yeah.
Yeah, expand the parentheses would be the first step. I actually asked you to find the larger solution here, which, I mean, for the small numbers, you can kind of guess and check what it would be, but let's actually just solve the problem. So you can actually see fully how we would have approached this. So if I have x minus 1 times x minus 2 equals 12, the first thing you would do is you would expand the parentheses. And then you would subtract the 12. You would end up with that. How do we proceed?
Can use the quadratic formula.
We could. That's an option. There's a nicer way. You don't need the quadratic formula. But yes, if you don't see what I would recommend to do, then you can always use the quadratic formula. Something a little more elementary.
You can factor it.
You can factor, right? So there's something called the zero factor property where you can, if you have a product of things equals 0, then one or the other has to be 0. That is in fact where this kind of error can happen here, because a lot of students try to apply that reasoning when they don't have a 0. So if they have a 12, they try to still apply, oh, if the product gives me 12, then one of the things must be 12. No, that's not true. Something like that is only true with the number 0. So if you see something that's non-zero on the other side, you cannot apply that reasoning. However, with 0 on that side, you can apply the reasoning. The idea would be you would factor. And then you set each factor equal to 0 afterward. What does this factor into?
X minus 5 and x plus 2.
Right. And so you can set x minus 5 equal to 0 or x plus 2 equal to 0. Because if you have two things multiplying give you 0, one or the other must be 0. This is called the zero factor property, which means your x is either 5 or your x is minus 2, and that's the larger one. So x equals 5 would be the response here. Final problem. Right, so I have 1 minus 4 over x squared over 1 minus 1 over x minus 6x squared. What do we do?
I converted the 1 for it to be x squared divided by x squared.
Okay. And then what?
And the 1 on the denominator, I did the same thing.
Okay.
And I multiplied 1 over x by x for it to have the same denominator of everything else.
Okay, so you're making a common denominator.
Yes.
Okay, so there's actually a way to do that pretty quickly. So there was a method that was recommended in class. Does anyone know how to get what she's trying to accomplish, how to get it done quickly? It turns out that you can multiply this by the entire fraction by something that'll achieve that.
X squared.
X squared. Well, you multiply and divide by x squared. Is x squared a random thing? Why x squared?
Because it's the prime factorization to the highest exponent. It's the
what you just described was GCF,
yeah.
Right? The greatest common factor. And the greatest common factor of the denominators is called the LCD, the least common denominator. happens to be the greatest common factor of the LCDs. So once you find the LCD, you multiply and divide by it. It's the quickest way to clear a situation where you have compound fractions into simpler fractions. So what you would do here is, of course, you take the x squared, you multiply the 1, and you get x squared. Take the x squared, multiply this. It'll cancel the denominator. So the numerator just becomes x squared minus 4. You'll notice that these are the numerators of the x squares that we were trying to create from before. You would do the same thing in the denominator. The x squared times that, the x squared times that, the x squared times that. So x squared times the 1 is x squared times the 1 over x is x squared times the 6 over x squared is 6, right? So you'll notice what these guys are. It would be like we had the x squared over x squared minus the 4 over x squared minus the x squared over x squared minus the x over x squared minus the 6 over x squared from someone who went through and created all the common denominators. But at the same time, we flipped and multiplied and canceled all in one shot. You can get all that done in one fell swoop with just multiplying and dividing by the LCD. So this is the method I recommend. So now you get here. What do we do now?
Factor it.
Factor. So the top is the difference of squares. The bottom, you do that thing where you come up with two numbers to multiply to give you -6. They add to give you -1. So something like a -3 and a minus.
And a positive.
And a +2. So now the x plus 2's cancel. And so we end up with x minus 2 over x minus 3. And of course, you should notice that your x cannot be -2 here because that would violate things. Anyway, so the simplification has an x minus 3 in the denominator, which is what I asked here. So that's that. So that's it. That's the entire quiz along with the bonus. So if you did not know that stuff at the beginning of the quiz, it's fine. You should start knowing a lot of that stuff now because of the lectures you would have watched since we dealt with these topics. But yeah, any quick questions before we go, because we're pretty much done with today? Okay. Well, that being said, we will stop there. Okay, thank you guys for joining. Thank you for your attention. Thank you for participating. And I hope you guys have the good rest of your day. So take care. That's it.
Thank you.
Take care, everyone. Have a good day. I will see you guys in the next one. Ciao.